Hello, my name is Jung Wook Lee. I'm a graduate research assistant working for Dr. Stein at the University of Illinois, and I'm going to be talking about effects of including tallow, palm kernel oil, corn germ, or glycerol to diets containing DDGS on pork fat quality of growing to finishing pigs. Today, I'll begin with a short introduction, then I'll briefly talk about how we conducted this experiment. I'll also explain what iodine value and iodine value product are. I'll present the results and end with conclusions. It has been reported that up to 30% of DDGS inclusion in swine diets showed acceptable pig performance. Currently, many swine producers are using greater inclusion rates of DDGS because there's been increased availability of DDGS in the market due to the greater production rate from the ethanol industry. However, it has been reported that inclusion of DDGS as 20% or more in the diet may result in soft belly production. A soft belly has undesirable physiochemical properties. High DDG inclusion results in poor bacon slicing, lean and fat separation. It is also susceptible to oxidation and therefore reducing shelf life. Overall, swine producers and packers may be financially penalized by these undesirable low belly quality and problems associated with soft belly production. Therefore, the first objective of this study was to determine if negative effects of DDGS on belly softness can be ameliorated by including tallow, palm kernel oil, corn germ, or glycerol in diets fed to finishing pigs. The second objective of this study was to test the hypothesis that IVP values may be used to predict backfat IV and belly fat IV of pigs fed diets containing DDGS. We used 6 dietary treatments. Diet 1 consists of corn and soybean meal based control diet with no DDGS and no added fat. Diet 2 consists of corn and soybean meal diet with 30% DDGS. For Diet 3, it is similar to Diet 2, except that we added 15% corn germ. Previous studies have shown that inclusion of 10% corn germ did not negatively affect pig performance and result in reduced iodine value of belly fat. Therefore, we increased the inclusion of corn germ to 15%. For Diet 4 and Diet 5, they are similar to Diet 2, except that we added 3% tallow and palm kernel oil to the diet. Tallow and palm kernel oil were the dietary sources of saturated fatty acids added to the diet. For Diet 6, it is similar to Diet 2, except that we added 5% glycerol to the diet. Previous European studies have shown that inclusion of glycerol resulted in lower IV and firmer backfat. A total of 36 barrels and 36 gilts with an initial body weight of approximately 43.7 kilograms were used in our experiment. There were 12 pigs per diet. All pigs were housed individually and pigs were allowed at libitum access to feed and water throughout the experiment. To answer the first objective of this study, gross performance data such as average daily gain, average daily feed intake, gain to feed, and carcass composition data were collected, and these data were presented at the Midwestern meeting earlier this year. For this presentation, I'll present the results of a belly flop test, which is a measure of belly firmness. A belly flop test was performed by draping a belly sample over a suspended stainless steel rod with the skin side down. The distance from skin surface to skin surface was measured at a standardized point, and this point was 10 centimeters down from the stainless steel rod for each belly. To answer the second objective of this study, fatty acid analysis of diets, ingredients, and belly fat and backfat samples were conducted to calculate IV and IVP of the samples. These are the equations that show how we calculated IV and dietary IVP. Iodine value is an indicator for the degree of unsaturation of fatty acids in that particular source of fat. IV was calculated using the equation from AOCS. There were two equations to calculate dietary IVP. Dietary iodine value product is an indicator for the total quantity of unsaturated fatty acids fed to pigs. The first equation determined dietary IVP1. Dietary IVP1 was calculated by multiplying IVP of each ingredient by concentration of each ingredient in the diet. The second equation determined dietary IVP2. Dietary IVP2 was calculated by multiplying analyzed IV of dietary lipids by concentration of dietary lipids and 0.10. This is the equation developed by Metz in 1992. Data were analyzed as a randomized complete block design using the PROC mix of SAS. The interaction between treatments and sex was not significant, so I'll be presenting only treatment effects in this presentation. Regression analysis were performed using the PROC reg of SAS to determine the relationship between dietary IVP and backfat and belly fat IV. For the results, let me take a moment to set up this slide. In y-axis are the response criteria, and belly flop tests were expressed in centimeters, and in the x-axis are the 6 dietary treatments used in this study. Yellow bar represents the control diet, green bar represents the DDGS diet, red bar represents the corn germ diet, the blue bar represents the tallow diet, the purple bar represents the palm kernel oil diet, the gray bar represents the glycerol diet. As mentioned previously, belly flop tests can be used to determine belly firmness of each pig. Therefore, a reduction in belly flop distance indicates belly softness. The flop distance was greater for pigs fed the control diet than for pigs fed the other 5 diets containing DDGS. However, there were no differences in belly flop distance among the diets containing DDGS. The results of this test showed that adding DDGS into the diet significantly reduced belly flop distance and therefore belly firmness. Addition of corn germ, tallow, or glycerol did not ameliorate the negative effects of DDGS associated with soft belly production. Therefore, we rejected our first hypothesis. Moving on to answer the second objective of this study, there are the IVs of the diets. As expected, the IV of the diets containing tallow and palm kernel oil were lower compared with the other 4 diets used in this experiment, whereas IVs of the DDGS, corn germ, and glycerol diets were comparable to the IV of the control diet. Here are the dietary IVP values calculated using the first equation. The dietary IVP of the DDGS diet doubled compared with the dietary IVP of the control diet from 28.9 to 53.6 grams per 100 grams of fat. When corn germ was added to the DDGS-based diet, further increased the dietary IVP from 53.6 to 75.7 grams per 100 grams of fat. The dietary IVP of the tallow and palm kernel oil diets were lower compared with the dietary IVP of the corn germ diet. The dietary IVP of the glycerol diet was fairly similar to the dietary IVP of the DDGS diet. Here are the dietary IVP calculated using the second equation developed by Metz. Dietary IVP of the control diet was the lowest, and the dietary IVP of the DDGS diet was comparable to the dietary IVP of the glycerol diet. Dietary IVP of the tallow, corn germ, and palm kernel oil diets were relatively greater compared with the other 3 diets. Here are the analyzed backfat IV. When DDGS was added to the control diet, backfat IV increased from 72.7 to 78.6 grams per 100 grams of fat. There was a huge variability within treatment groups. Therefore, we were not able to detect any differences in backfat IV among the treatments. Here are the analyzed belly fat IV. When DDGS was added to the diet, belly fat IV increased from 74.9 to 79.5 grams per 100 grams of fat. Belly fat IV of pigs fed the other 4 diets ranged from 75.4 to 79.1 grams per 100 grams of fat. Again, we did not see any differences in belly fat IV, and there were no effects of dietary treatments on belly fat IV. This slide shows a relationship between the dietary IVP calculated using the first equation and observed backfat IV. Backfat IV tended to be positively correlated with dietary IVP1. Using this calculation, IVP1 explained 63% of the variability in observed backfat IV. Using dietary IVP1, backfat IV was predicted with the following equation presented in this slide. Using the second equation, we had R-squared value of 0.52. Therefore, our results show that dietary IVP1 and dietary IVP2 explained more than 50% of the variability in observed backfat IV. In US, the bellies are more premium cuts sold in the market. Therefore, we wanted to know if dietary IVP equation used in Denmark to predict backfat IV can also be used to predict belly fat IV. This slide shows the relationship between dietary IVP1 and belly fat IV. Using the first equation, there were no relationship between dietary IVP and belly fat IV. Again, there were no relationship between dietary IVP calculated using the second equation and belly fat IV. Therefore, our results indicate that belly fat IV may not be predicted by using either dietary IVP1 or dietary IVP2. Conclusions: the negative effects of DDGS on belly softness were not ameliorated by including tallow, palm kernel oil, corn germ, or glycerol in diets fed to finishing pigs. Dietary IVP was not a strong predictor of backfat IV. Dietary IVP may not be used to predict belly fat IV. If you're interested in more swine nutrition topics, you can visit the website nutrition.nsi.illinois.edu. Thank you for your attention.